Good afternoon, everyone. Good afternoon. Thanks for that. Yeah, Jose. I mean, in India we call ours of Jose, and this is Jose in US as well as in Spain. So it's good. So I'm part of Black Pepper Technologies. So a little different from the institutions where the research institutions. We are a end-to-end silicon and system design company with an ID capability, focusing on quite a bit on the sensor fusion algorithms and all. So myself, Tinku, Malayil, Jose, or Jose, whichever I am okay with both. And I had the embedded software group in Black Pepper, as well as I have my colleague Roshan. So this is actually about sensor-based predictive maintenance on motor systems, basically machines, basically. And when we talk about it, the biggest challenge which we see is what we try to achieve is that a system which can diagnose machine behavior and characteristics using sensors, basically. That's one. It should not be non-intrusive. It should be, it can actually fix it to any kind of motor. So that's what we want to achieve. Adaptable to any position, access, wherever we keep it, it should be able to learn and do it. And mainly, the only requirement will be it should be able to detect the vibration. And one of the things the reason why we are looking for such a system is specifically for, newer systems, newer motors will have these sensors already embedded, and there will be various algorithms which is already running. Whereas in the case of older systems, and there are quite a number of them which do not have any kind of sensors which is there, and to fix it, retro will not be a feasible option. It will be quite costly, as well as there will be a lot of downtime. So what we wanted to achieve, or what we wanted to develop, was something which can be retrofitted, maybe fix it somewhere outside the casing, detect the vibration. So that's what we try to achieve here. So it's our overall system. What we are trying to achieve is anything, any input. We call it as a disturbance because it can have the valid data as well as invalid data. The invalid data will certainly become valid at some point. That's the reason we call everything as disturbance instead of saying everything as valid data. This can be sensor, and we do some conditioning of the data, do filtering, get whatever the relevant data what we want, and do a fast Fourier transform, and get the impulse response what we are looking for specifically for those data. Where we realize the system, and where we model the parameters based on the place where we place the sensors, and and devise a model which will actually get the get the information what we are looking from the models what we keep getting, in fact. So, and this can be utilized for analyzing the faults in a system, or you can actually find what is the best way, what are the best options to actually find whether it is running in the optimal parameters and things like that. So this is what the high-level overall system. I'll just quickly get into what is the solution approach. So, what we are trying to do is that get a accurate impulse response for a frequency domain from these sensors, basically, and then detection of when we want to do that, you have three-axis accelerometer which we are using. So we'll have to actually identify which is the dominant vibration axis. Then we have to remove all the gravity as well as all the high frequency components and all the bias using. I think we can use high pass filters for that and get only whatever we want. And since this can be used as a retrofit device, it has to detect various positions where these sensors are actually kept, and we have to identify these parameters for those areas as well, in fact. So it can, if you have a motor, it can be kept in the X or the Y, or somewhere in the behind, wherever it is, and for each of these axes, we need to figure out what is the impulse response. Now, edge analytics is what we are trying to do, because this is something because there are a lot of IoT systems where we just get the sensor data, send it across to the cloud, to the backend or the gateway, which is having much powerful system, analyze it, and then give notification. But usually by the time there can be some events which will be missed, in fact. So what we are trying to do is that we're doing an edge analytics part of it to do whatever is needed specifically for that system to find whether the system is working fine or not in the edge itself, which can be a very low performance kind of a system. It can be a sensor with just maybe a very, very low MCU which will be available with a wireless communication module. So in that scenario, we need to identify and tap into all the computational power which is available in that small sensor module and the communication module, and try to make some meaningful data which can be used for immediate responses or immediate notification. That's what we are trying to do with this. So it can have DSPs, it can have MCUs, it can have various processing units, and based on that we will be able to do it. One thing is clear, it will not be a very powerful system. It will be something which is operated on battery and things like that. Then once we have this data, we can send that data to the to the gateway using one of the PAN networking technologies. Then after that, it can be advanced analytics, and all those computation can be done in the backend for further information. Now, another thing which we have to do is also trying to figure out various motors will have various responses, and how to figure out that. So that is where we try to use machine learning or deep learning algorithms with some intelligence added to it, and for identifying what are the various values which need to be compared with, in fact. So these are actually the pre-processing which will happen based on the motor parameters. So if you don't have the parameters of the motor available already, run these algorithms, get these parameters, populate it, and use that. Or from the motor manufacturer, if you have the parameters available, use that directly. So we have to cater to all of those, in fact. And already mentioned about the lack of processing which will be available, and that's where the heterogeneous compute part of it will come in, which is mentioned in the title itself, in fact. So from here, I will just quickly go into an experiment which we have done, and we are actually demonstrating this in our booth in the courtyard. It's basically what we have done is that a table fan, a simple table fan, which is manufactured, it doesn't matter which brand or whatever it is. It's a 3-speed commercial table fan is what we are used, and attach the sensor device on the covering of the fan, and try to the way we are identifying the RPM frequency responses and all is to try to figure out what speed or what RPM it is running from the frequency responses. The only thing which will be attached to the fan will be an accelerometer with maybe a Bluetooth. It's not needed, but still we can use some LEDs to blink, but we try to plot it over to have a good look or feel. We plot it over so this. So it's actually, we did the complete algorithm in a Cortex M3 with 48 megahertz. Accelerometer was a 2 gig to 16 gig accelerometer, and communication used for plotting was a BLE. So even though we had this as an IMU sensor, we use the primary sensing element as accelerometer. We can use the other sensors for fusion, and Cortex M3 with MCU, which interfaces with the accelerometer and performs all the computations needed, and vibrations are analyzed and processed in frequency domains to characterize the motor and machine, how it is operating, and all of those. Quickly get into the system architecture. So the way it is, you have an accelerometer, sensors, it is converted to an ADZ, and in the system, in the MCU, we will have the real-time system which is running, which is getting all this data, a communication stack which is critical to send the data to the gateway and to the cloud from there, and emission monitoring condition and an algorithm what we have developed which will be running there, which will provide some indicators immediate indicators or notifications to the maintenance crew of whoever it is. So this can be potentially used for predictive maintenance. So in this experiment, this is the architecture. You have the buffers which will be coming in. One of the first is to detect the vibration, which is the dominant axis for the vibration. Then remove all the bias from the data, clean it up. Then you pass through. We have the high pass filter, and then normalization into a window, and then we do a FFT. Once we have that, then we have a frequency which is available, and then we can actually convert those frequencies to a bin, and from there we can actually arrive at the RPM and the speed at which it's running, in fact. So this is what the overall architecture. So accelerometers, it is generated all the 3 axes we get it, and there can be gravity present, so that has to be removed. Yeah, sure. 2 minutes, okay. At the time here as well, sorry. Okay, and frequency spectrum plot and the motor vibrations. It actually we will be able to get what are the major frequencies which will be running, and yeah. There will be apply all the biases, all the gravity and biases are removed using, and then high pass filters for only getting the high frequency components what we have. And when we get the peak and the RMS plot, and finally we do FFT, and as per the spec, what we had for one of the fans was it was actually 1280 RPM is actually the speed spec, and based on our frequency analysis, we got into 22.89 hertz is actually the frequency which came and we translated to 1289 RPM. So this is what this is how we were able to get the RPM from the frequency just based on the accelerometer, in fact. So it can be further improved, and you can actually increase in the FFT size and all. So just a quick analysis for speed 1. This is again a table fan resistance. Speed 1, it's actually to 990 RPM, which is actually what it is. We are able to estimate that. Speed 2 for the next one, and then speed 3 is 1289. So this is the way we are able to analyze all these three speeds. This is a way to prove that using acceleration we'll be able to get, and wherever it is placed, in fact. So conclusion: predictive maintenance of equipment is possible by real-time vibration analysis. That's the first thing which we wanted to do. And machine monitoring system, it should be non-intrusive. And we can actually leverage various computational units in the system, in the sensor or the communication system, to ensure that tap all of those and get a heterogeneous solution up and running. And one of the future work we are doing is actually doing a machine learning identification for acceptable limits for different kind of devices, basically. So that's all. I think any questions. I have my colleague Roshan also here who will be able to